I should.
Okay, Terry, please.
All right, I'll continue now with lecture 4, which has a title I made up. I like variational, and I'm going to be speaking about various kinds of convergence. There is something called variational convergence, which is a subject that was invented by Italians in the theory of partial differential equations. That has to do with infinite dimensional spaces, but it corresponds to what I will call epiconvergence in this talk. But convergence is also involved with approximation. And I wanted to put all these ideas together and explain to you why these concepts of convergence and continuity and things like that are absolutely essential, even in the study of generalized differentiation and non-smoothness. And so to go back to this a little bit, let's take this grand view of this subject that what we learned in calculus. Let's go back to what we had in calculus. We know that we have the concept of a function, we have the concept of a function being differentiable, and then we have all those important rules, the derivative of the sum of functions, the chain rule, all of those things in which we are showing how differentiability works with various operations. The operation of adding functions, composing functions, multiplying functions. But what an operation which does not exist in classical calculus for this purpose is taking a minimum or looking at the argmin in an operation. So this is one of the things which is the contribution of variational analysis. So bring those operations into a kind of calculus. So for this perspective, we want to start very generally. Adopt a point of view where we are minimizing just a proper lower semi-continuous function on all of Rn, and the constraints to the extent that we have them in this thing, they're just represented by the effective domain of that function. That may or may not be a closed set, even though the function is lower semi-continuous. And then I want to associate with that function, first of all, is its greatest lower bound, the infimum of this function. That could be minus infinity. That's okay. The infimum, or some finite amount. It can't be plus infinity because I'm assuming the function is proper. And then I want to associate the set of points where that infimum is attained, if any. This might be an empty set, but I follow the convention that if there are points where this infimum is attained, then I can write min f instead of inf f to indicate that. Now, well, that brings up a simple question right from the start, which also shows a different philosophy here. How do we know that there is a minimizing point? So everyone studies in advanced calculus this classical criterion, which is what most people appeal to when they ask this question. How do you know that the function attains its minimum? They think of it in terms of minimizing a differentiable function, or at least a continuous function, over a set C, a closed set C. And if the set is compact and the function is continuous, then the minimum will be attained, but also the maximum will be attained. This is a symmetric theory in line with classical thinking. Everything should be symmetric between minimizing and maximizing. That's not my philosophy here. So that gives a criterion if you're minimizing a continuous function on a compact set. But that's not good for us because we need to talk about unbounded sets. What about minimizing over all of Rn? What if you had constraints representing the set C, but then you replace those constraints by some penalty approximation of the constraints? So we have to be able to deal with minimization in a different way. And the way to do it is to use the boundedness of the level sets of the function. So we have this general criterion that if the level sets, there's the lower level sets where it's less than or equal, that if there's one of those level sets, remember all these level sets are closed because the function is lower semi-continuous. If there's one of those level sets which is above the infimum and it's bounded, then the set of minimizing points, global, these are global minimizers. Local is another kind of thing that we're not getting into here for this part of it anyway. that will be a non-empty compact set under this criterion. All right, so here, if we are limiting ourselves to such functions, suppose I'm looking at functions that have this level set, then with each of them, I'm assuming I am assigning two things. I'm assigning this argmin set and the min value. So I can think of these as operations on the set of functions. In one case, I have a set valued operation for assigning the argmin, and in the other case, I have a numerical function assigning the minimum value. That's being finite also, by the way, in that case, a finite value. And then so now I have this question, how am I going to handle these? I want to think of these as operations on functions and manage to deal with them in the sense of calculus. For example, I can remember that at a certain level, it was interesting to me that you could define a new function by an integral in terms of some other function. That's a more advanced than just defining a function in terms of the chain rule for its other functions, for example. You could define it by an operation like integration. Well, we can define new functions by minimization. We can have a function in two variables and minimize in one, and then we have a residual function in the other. So here's an example of this being an operation that we need to deal with in a generalized kind of calculus. And then certain kinds of continuity issues will come into this. And that's the kind of thing I'm going to address at the beginning. To what extent could these operations have some sort of continuity property? So this would depend, of course, on how we imagine the functions. When is one function closer to another? We want to know that. So what kind of conditions? Suppose we have a sequence of functions, and we imagine these functions, f nu, indexed by nu. These functions f nu are converging in some way or other to the function f. Then the question is, will the argmin of f and the min of f be approximated by that of the functions f nu? And what does it take to make this be true? So the traditional approach to convergence of functions on Rn is to look at finite functions. And there are two main ideas that get used. One is that you have the pointwise convergence. That is, at every point of the space Rn, the value of f nu at that point will converge to the value at f at that point. That's pointwise convergence. And then there's the higher level version called locally uniform convergence, in which I look at bounded sets and I ask that this pointwise convergence be uniform. In other words, I look at the uniform norm over each bounded set, and that norm should go to zero. I take the maximum difference should go to zero. For every bounded set and every epsilon, there should be a high enough nu so that the differences are below that epsilon. And in the case where these functions are Lipschitz continuous, all with the same Lipschitz constant, then these two kinds of convergence are actually equivalent. That's a valuable thing for many purposes. But here's the trouble. This doesn't help at all with the kind of issue we want to address. Pointwise convergence of these functions would mean that where the value of the function f, where f is infinity, these things have to go to infinity. And then, well, it doesn't actually, it's not quite right what I say here, but it would require that the effective domain of fn of f nu be has to include the effective domain of f. And anyway, these locally uniform convergences can't handle these infinity values. What do I mean by the difference between them? So it turns out, though, that what matters is that we have to see how the epigraph of the functions will converge. And so I need to explain that a little better. So here's an illustration of the needs of this subject. So imagine, just as the reference point, that we are interested in minimizing a function f0 over a set C, but this is just a special case. I have this closed set C, and I'm minimizing, let's say, a continuous function over this set C. I might want to approximate it. And approximating this could be done by replacing, I can think of this as minimizing the function over Rn that's given by the sum of this f0 and the indicator of C. But then I could approximate the indicator of fc by from the outside or the inside. So in the first picture, I'm approximating this indicator by, instead I'm adding some sort of penalty. I have a penalty expression that I'm adding to get the function f. So there I have my approximate functions that I'm getting are outside. They give epigraphs that are bigger than the given epigraph of f over the set C. But I could also be doing it inside with so-called barrier functions. So here's, remember the function f0 is this thing down here, but I'm making internal approximations in which they kind of go up to infinity as I get nearer to the boundary, and they could get closer and closer to f. But these approximations are certainly not converging in any kind of a uniform pointwise sense or anything like that. And then it's not always obvious, but here's a simple example that shows what the kind of trouble could be. If you just have continuous, even if you have a compact set, we're just looking at a compact set C, and I'm looking at continuous functions on this compact set C. And here's my function f nu, and it has a 0 at this point, but it always has a value 1 there, and it is this obvious construction. And now as nu gets bigger and bigger, this little v gets sharper, this shape gets sharper and sharper, and it goes over here. But in terms of pointwise convergence, in the limit, the pointwise convergence is this constant function. So if I just look at the pointwise convergence, I would get a completely wrong answer as far as optimization is concerned, because the minimum is always 0, and it's at this point here. But in the limit, the minimum is 1. The minimum or the limit function is 1. So the operation of the minimum is not continuous with respect to this kind of convergence of functions. But if you look at this is come in a little later, if you look at the epigraph of this, so as this point goes farther and farther over here, this gets sharper and sharper. And what will I have as a limit? Instead of just this epigraph up here, I will have this epigraph along with this little line segment. That would be the epigraph of a discontinuous function, which has a jump at this point. But the minimum would be 0. So some of this illustrates why epigraphs somehow are needed to capture behavior that pointwise convergence, even if uniform, does not well capture. So this leads us to set convergence. This is a subject with a long history, but much of the history has been somewhat misguided in the sense that it was always limited, or the focus of it among pure mathematicians was very general in, like, let's treat very general topological spaces. On the other hand, everything was supposed to be compact. So almost all the literature on it is that way, except that some people did look at more generally, Henleve, and followed by Kuratowski, a famous Polish mathematician. And so here's the idea. We can always, making the sets be closed is a fairly harmless assumption, and I won't go into it. The limits are always going to be closed anyway in the subject. So we can have two kinds of limits when we have a sequence of closed sets: an outer limit and an inner limit. And I'm going to illustrate them. First of all, let's look at this picture. Here's going to be a simple, we have a good intuition, actually. This is one of those miracles of the human mind, again, with geometry. We have a very good intuition of what it would mean for some sets to converge to each other. Like here I have some sets, I have a whole sequence of sets here, and they're getting closer and closer, and then the limit, they get this set. So we can see in a moment how we would quantify that to make this work, to make our intuition into some mathematical formula. But we want to look at this more generally, where first of all, and let's look at this sequence where I have like alternating sequences. On each side, the thing gets narrower and longer and narrower and longer and narrower. Now, in some sense, when you look at everything that could be approached without being final necessarily, you could get the whole line this way in the limit. But in a more narrow sense, it's only this point that you're getting. That's kind of common because so we have to capture that by definitions. So we have here the outer limit, which is written with this lim sup. And this consists of all the points, like here's an example, that you could reach by looking at some subsequence of the sets and selecting a sequence from that subsequence, a sequence of points that converges here. So this point, for example, I can obviously reach by a limit of the sets here, but these sets aren't involved. So it's only the subsequence of sets over here that would give that. That's the outer limit. All possible things you can reach as cluster points of selected subsequences from these sets. But then the more stringent definition, the inner limit, written with this inf, consists of the ones such that once the nu is high enough, all the sets can be divided. So I get a selection that's in every set. There are no missing sets. A selection, and that sequence converges here. And in this picture, only this point here has that. For every nu, I can get a point in the set C nu that gets closer and closer and so forth. So, and then we say that we have the limit when both of these coincide. So we look at all those, but every limit we could actually get in a stronger way that's described here. And right now, that's a sort of a formulaic way of looking at it. But the intuitive concept that we have here can be understood very nicely in terms of the distance function to the set. So let me just take a point here. I'm looking at a little point X, and I look at this. I can look at the distance of this point. I look at the distance of this point from the set C1, the distance set C2, and the criterion is that this distance should converge to the distance to the limit set. And if this happens for every X, the distances converge for each fixed X. That's equivalent to this definition of limit. There's also a way to describe the lim inf and the lim sup this way, but I'm just focusing on this. This is the easiest way to understand what set convergence consists of. And now I want to remind you that historically the trouble was that because of the focus on compactness, they had a different. Everybody agrees with the lim inf, and they call it the lower lim or the lim inf. But people disagree on this, and they want to call it the upper limit. Lim sup, but they use a wrong definition that's not suitable for our purposes. So I've tried to insist that we shouldn't use a lim sup and lim inf. I mean, inner and upper and lower. We should use outer and limmer. And it's not just a question of taste. It's a question of getting the wrong idea if you look at lim sup from the way that you traditionally will see it defined. Right now, our purpose, though, is to go on to functions because we're working with things like what happens to min and argmin. So now I'm looking at lower semi-continuous proper functions on Rn. Of course, what that means is I'm looking at a certain kind of sets, looking at the epigraphs of these functions, which are certain closed sets in Rn. And then I can ask whether these sets converge. There could be an inner limit, there could be, an outer limit, an inner limit, an outer limit, but let's just for the moment speak of the limit. When there's a limit, what are those epigraphs going to converge as sets? And that's what we call epiconvergence. And then there's this notation here, that converge, there's a little epi I write above here to show, at least for this talk, to show that I mean epiconvergence. So that's exactly the definition. Well, this is a geometric definition. As in with many things in mathematics, there are equivalent ways to say the same thing. And some people use one of those ways as a definition and then prove the equivalences. Other people start with a different version of the definition and then prove those equivalences. But this is what it means geometrically. And that's what I want to concentrate on in trying to convey these ideas in this talk. But here's how it would look if you need to verify it. You know, how are you going to look at it? Are you going to construct the distance functions to these sets and converge them? That would actually be a difficult way to handle this. It's much easier to use the following kind of criterion if you're really trying to verify that something epiconverges. And it means that at each point X, you have to verify two things. One is that for every sequence approaching this set, the lim in forward that sequence cannot be less. But then you have to combine that with the fact that there is at least one sequence for which the lim sup is not more, in which case it has to actually be equal on the basis of the first property. So those are the two things typically you would verify in showing that your sequence epiconverges. Well, why do you want to do that? Okay, I've tried to motivate this as here's a good idea, but now comes the key theorem. This is the key big reason why this is the right concept for variational analysis, is because of its application to optimization and things like convergence of algorithms, numerical methods. Because those methods are often based on approximations. Instead of minimizing, solving the given problem, I solve a sequence of approximate problems. But each of these problems is represented by a function, f nu. And then the question is, do those functions, anyway, we can use this epiconvergence. So now I make an assumption that it's a level bound in this assumption, but it's going to work for all the functions beyond a certain point. We'll have equally, the level sets will equally be bounded. For some value c greater than the infimum of f, all these things have bounded, or equally bounded, which means, by the way, that the minimums of all these things occurs. And then the conclusion is that if these are epiconvergent, then the minimum values will converge, and then that the outer limit of the argmins will be included in this. So there will be, and this will be non-empty. Maybe you should have said that. This will be non-empty, and every because they're all uniformly bounded here, and every point that's a cluster point of these will be in fact a minimizer of the function f. And that's an application of this epiconvergence. So without this, you get all those weird properties that I was describing earlier, and people have a difficult time showing how min and argmin behave as operations. Now, here's some examples of epiconvergence. So suppose we are on here that we approximate this. We have a function, and let's look at this thing where I'm minimizing a function f0 over a set C, which is closed. And it's a continuous function on a closed set. Minimizing a continuous function on a closed set. Then suppose I want to approximate by a different function f0 and a different set. And now what's important here is this set could be bigger or smaller, I don't care. It doesn't have to be the same one way or another. And then the criterion I get from epiconvergence, which I could verify in the way shown there, is if these functions converge locally uniformly, that is unbounded sets locally, and if the sets converge as sets, then this function will epiconverge, and therefore I will know that in my approximations, the minimum value will converge to the minimum value in the limit, and any solutions that I get from the subproblems will be bounded, and their limits will be solutions to the true problem. And in particular here, we have this simple but important property that a sequence of sets converge if and only if the indicators of those sets epiconverge. Now, here's really a remarkable example. A remarkable example of the power of this concept of epiconvergence. This goes to convex analysis. My favorite topic in convex analysis, as everywhere, is duality. Duality. And in convex analysis, duality is expressed by conjugate convex functions, but they're also a tool not just in giving you different problems, but for example, in defining augmented Lagrangians, and there's so many things, special cases, polar cones, and so forth. So conjugate functions, I have two closed proper convex functions that are conjugate to each other. And you remember that they're given by this formula that if I have this function f, then I define its conjugate function over here. And then from the conjugate function, I get back the original function f by the same formula. An amazing operation, which has a background in classical theory as the Legendre transform, and also in functional analysis as the Young conjugates and so forth. But it was Werner Fenchel who put it in a more general plane. He didn't do it with infinity value functions. That was left for Jean-Jacques Moreau and me to translate it to that. But anyway, so you have this conjugacy. But so this is an operation. This is a transform in which I take a function f from a certain class and associate it with another f in that class. Is that transform continuous? Well, to ask that question, you have to say what topology you should use. So I've been talking about epiconvergence, and I've not approached this formally as a topology, but it is possible to set it up as a topology. It's a metrizable topology. So there's a topology, and here's the amazing thing about that, this is exactly, epiconvergence is exactly the kind of topological topology on a space of lower semi-continuous proper convex functions under which this transformation is continuous. And here's something almost equally amazing. Who discovered this? Jean-Jacques Moreau, myself, somebody else? It was discovered by a statistician, Weissman. A statistician, to this day, I'm not quite sure why he was so interested in that, but he was. Maybe there was some application in statistics, but he came up with this very, very beautiful fact. Later, it was approached in a somewhat different way. So let me just say that as a special case, this includes things like the following. Suppose you have closed convex cones K, nu, that are approaching a closed convex cone K, then that is equivalent to the polar cones approaching. So here we're looking at just set convergence, and that's because the polarity of cones is represented by conjugacy of their indicator function. So at a somewhat later stage, Roger Wetz and his collaborator David Walkup proved that set convergence gave this equivalence. And then from this equivalence, actually, you could derive that, but then they discovered, to their misfortune, that it was already been proved by Weissman. So there's already was just a special case. All right, now we get to graphical convergence of mappings. As I was talking about epigraphical convergence of functions, but now I'm going to have to look at mappings. And one of the reasons is that I want to look at subgradient mappings. How can I relate epiconvergence of functions with what happens to their subgradient mappings? So let's approach this again generally. And luckily that's the benefit of starting on such a very general level. We are talking about the convergence of closed sets. Well, those closed sets can therefore be the graphs of mappings. Mappings, as we know, can be defined here. Mapping from Rn to Rm can be defined by any subset of the product space. I can take any subset that could be the graph of this, and then mappings can have a closed graph. These are mappings actually which would be outer semi-continuous at every point. And then the mapping has its effective domain, and then the great advantage of this generality is you don't have to worry about whether inverse exists. It always exists by definition. You just reverse the pairs. U becomes a pair UX to get the inverse. All right, but what are you going to do with this in the classical way? The classical theory is all devoted to single valued mappings, F and F nu from this one space to the other. And then those mappings, as I was describing earlier, they can be studied in terms of pointwise convergence or locally uniform convergence. And that just isn't good for set valued mappings for all those reasons. For example, what are you going to mean by pointwise convergence? You could imagine that this would mean that this set of Zeta sets, but if so, then the domains would have to be the same, because how is this going to, I don't know, the x's, all the mappings would have to have the same domain. Well, that's not good for us. And what locally uniform convergence, I'd have to understand what I meant by this definition. Okay, I could use some sort of distance expression for this, but still, I'd run into trouble when the sets are unbounded, especially. But they also, then what about the domain? So these classical ideas are useless, really useless for the subject. We have to have different ideas. But set convergence gives us those ideas. So very simply, we can say that a set-valued mapping, a sequence of set-valued mapping converges to another set-valued mapping if their graphs converge as sets. And of course, then you could have an inner limit, you could have an outer limit. These can also be helpful. All right, now we get to things that are, actually we're getting so many results that are coming in here now, which I just find amazing results that are just extremely beautiful and powerful. So surprising. And in the history of mathematics, people didn't think about this kind of thing. This is the subject that has arisen from optimization as elaborated in convex analysis and now variational analysis. So now there's a concept that was discovered independently by people working in partial differential equations back in the 60s. And but then this is my early days, as I was just early PhD in a kind of like just postdoctoral phase, I realized that the subject was really part of convex analysis and could be pushed much more than anybody knew. So this is the concept of monotonicity of a set-valued mapping. Now, and this is actually, it sounds like monotonicity should be related to some sort of ordering, but it's actually more a generalization of positive semi-definiteness in a sense. And it's a big and important, interesting subject, with many surprises, but you can't look at it here. I just want to give this definition, and it is that if you look at any 2 points in the graph of this mapping, and then I take the differences, then the inner product has to be non-negative. And then you could ask for maximality of this property, which means that you could, there's no way to enlarge the graph without destroying this property. Then you have maximal monotone graph, and this is somehow very closely related to convex analysis, and you'll see immediately why. So here's a result of one of my former students, René Paulequin, French-Canadian, who lives in Alberta, Edmonton, Canada. And this has to do with the monotonicity and subgradient mappings. Now, I should say, first of all, it was obvious to me and Jean-Jacques Moreau and other people that if you had a convex function and a subgradient mapping, then that subgradient mapping would be monotone, even maximal monotone. So we knew that, but what did Paulequin do here? He added, he worked with where the function is not necessarily convex. So in his case, we just look at a lower semi-continuous proper, we're not assuming any convexity here. But this function does have a subgradient mapping. We've defined it. There is a subgradient mapping, and you could ask whether this subgradient mapping would be monotone. And we know that if the function is convex, it's monotone, but what about the converse? He proved the converse. So surprising. So if this is monotone, then the function has to be convex. And moreover, since it's a subgradient mapping, monotonicity automatically entails it being maximal monotone. So this is a characterization in terms of this monotonicity property of subgradients of which functions are convex. Quite remarkable. I also have other characterizations I worked on, cyclical monotonicity and so forth. But this is what talks about what works for us here. If we already know that we have a subgradient mapping. And here's a picture. This is just a one-dimensional picture, but here we have a piecewise linear kind of mapping. It's a function, and its epigraph here is polyhedral set. And then the the subgradient mapping associated with this has these little jumps. These little jumps correspond to the fact that the wiggle room that I have a range of subgradients here, just different slopes at these points. And at this end, I have, this goes down infinitely, and this goes infinitely off horizontally. And so this is a maximum monotone mapping associated with this. And anyway, that's a convex picture. All right, now we get this other result. This is a landmark result proved by a French colleague who later did a lot of work on all this kind of convergence theory that we're discussing with Roger Wetz. And they proved many of the main theorems in this entire subject of set convergence, epiconvergence, and how to apply it in optimization. And he had a result that was in his doctoral dissertation that he finished in 1978. And this is still perhaps one of his most famous results, although he's done many other things since then. And that was, it's basically a result in convex analysis, but it's just truly remarkable. It shows how you could characterize here. On the one side, I have an equivalence. On the one side, I have that the functions are converging epigraphically. F nu is converging epigraphically to F. And on the other hand, I have that the subgradient mappings are converging graphically. And also one extra condition. Why an extra condition? Well, when you pass from the F's to the subgradient mappings, you lose a constant. You lose a constant to go back. You need a constant of integration, let's just say. You lose something when you go there, because if you change a function by a constant, you get the same subgradient mapping. So you need this sort of something to tie the values together. So we have to assume that there exists a sequence of points such that the function's values converge to the value at that point, which is finite. So we get this if and only if condition. And this ties the epigraphical convergence to the graphical convergence. And you can see here too that you could imagine functions converging to this function. For example, I could imagine rounding off. What if I didn't like these sharp corners? So I do some little interpolation to round off those corners. What would that look like over here? It would mean that I would be replacing these little vertical segments by little slanted segments that get, and in the limit, those get steeper and steeper. So in the limit, they do converge. It only makes sense that they converge graphically. It can't be any other kind of convergence. Convergence of the epigraphs corresponds to this graphical convergence. All right. Now, here's what we're going to start to do with this. I'm still aiming at second order theory. So now that we know what it is for convergence of mappings, I can define derivatives of mappings. I can do it as follows. So I'm looking at some set valued mapping here, and it has a graph, and I can define. Okay, this graph, I can take a particular pair. I'm looking at a particular pair in the graph. Because I have a set valued mapping, an X is associated not with some unique M of X, but I have to choose something in there. But once I choose that, then I could look at the graph. Okay, here I'm over here. I'm looking at the graph, and I'm looking at this point in the graph, and there's a tangent cone at this point. That tangent cone is the subject to the product space. So therefore, it is the graph of some mapping. And I define that mapping to be the graphical derivative of M at X bar for that particular value, U bar, in M of X bar. And now the way to look at it that seems a little more familiar, perhaps, is to look at difference quotients. So now I can look at, for tau greater than 0, I can make a difference quotient as follows. I take at X bar, I take this, for a given W, I take this plus W and subtract U bar. Now, classically, you would maybe want to put here M of X bar, but we don't have M of X bar. We have a particular U bar in M of X bar, and then I divide by this tau. So that's the example of the difference quotient. And this is a mapping, which associates with each W that. And then I can ask, when do those mappings, how do they converge? And so anyway, this definition means that the graph of this derivative is the outer limit. And we can also look at the case where the outer limit is truly a limit, and that's called the proto-differentiability of that map. I'll use this concept in a theorem that's coming up, a very interesting theorem again. So this is, so look at that. We can take any set-valued mapping and we have a concept. There's also another kind of thing using normals, but I don't have time to discuss that in these lectures. Those are called co-derivatives, and they're also very interesting and important. But right now, what I want to do is get on into the second order variational analysis. And well, what should it be? I think it's good before we look at how to generalize this second order theory to look at what the classical framework is, to remind us of the characteristics that we have. So what we have for a function, first of all, we have the first order derivative, and this is where I'm taking the gradient of it, and how is that characterized? The gradient is a vector, the unique vector v, if it exists. It's the unique vector v such that I have this linear, this is supposed to be a plus here, a plus. Sorry, should be a plus, plus this error term. This should be approximated by this plus this with an error term. That gives the first derivative. Then on the second order, we're looking at a matrix. It's an n by n matrix, a Hessian matrix. So I'm calling it H for Hessian. And it corresponds to a first order approximation of the gradient mapping. So it's like differentiating, and indeed, you are differentiating the gradient mapping. In that case, then, you also have, classically, that you have this second order expansion, then that this function has a second order, it's equal to this quadratic function in W plus a second order error term, which you could also imagine looking at the second order difference quotient and seeing if there's some you could somehow recover the Hessian matrix from asking about that, and that's all pretty well understood. And it's all connected with directional derivatives in the sense that this gradient is obtained by looking at limits of this kind of difference quotient, and a Hessian is in terms of this kind of limit of difference quotient. So how are we going to deal with this now? Because we want to go in to look at extended real value functions. This is no longer R, this is R bar. There could be infinite values here. Furthermore, the gradient now is a set valued mapping. So in this case, here I was making some approximation of the gradient mapping to get the Hessian, but if I try to imitate that, then I've got a set valued mapping. What do I mean there? So this becomes confusing. But I could maybe think of this. I could, well, here I would have to put in some subgradient maybe, but I could think of some kind of second order difference quotients. That's what we'll actually be looking at. But it'll turn out that we can do things in both ways. So somehow we got to do with that. And then, as I say, even if we do this, we're dealing with values that are infinity. So suppose I try to imitate this, a second order thing. I'm looking at a second order difference quotient where I could put in a particular subgradient here, let's say. I still have these as infinite values. I don't necessarily just want to take a limit on lines. What would I want to take? Well, an epigraphical limit, of course. We can't even talk about second order theory in any really legitimate way without using set convergence by way of epigraphical limits. So that's just what we'll do now. Okay, so here we now have a proper lower semi-continuous function. You can have its infinities. And I'm looking at a particular pair in the graph of the set valued mapping, which is a subgradient mapping. And then I can set up these second order difference quotients. So these are the things I'd like to, this is my Hessian type thing. So just as before, I have to put in here a particular V bar. And then I get the second order difference quotient. And it's interesting to notice that here, that if you take the subgradient mapping of this second order difference quotient, then you actually get the first order difference quotient for the subgradient mapping. A moment ago, we looked at first order difference quotients for set value mapping. So these agree here in this case. So we're going to define now second order epiderivatives with the idea that we take now it's just going to be the lower limit, the lower epi limit of these functions. And in the case where we actually have a limit, okay, so what this means is I'm looking at the case where if I look at that this limiting thing that I'm calling the second order epiderivative function, its epigraph is the outer limit of the epigraphs of all these difference functions, second order difference quotients. But it could be that this outer limit is in fact a limit. In that case, we talk about the function being twice epidifferentiable at this point. And now here's again a remarkable fact, but we wouldn't be able to know this without that result of a touche about how the epigraphical convergence of functions, convex functions, corresponds to graphical convergence of their mappings. Now, all of these functions are zero at zero, so we don't have to worry about fixing a constant of integration. And we get this result that this function f, it's convex function now, is twice epidifferentiable if and only if its gradient mapping has this protodifferentiable property. And then this is a kind of formula that is central, but it has a form that people don't fully grasp at first. But it says that the graphical derivative of the subgradient mapping is in fact the subgradient mapping for the second order epiderivative function. Okay, is this very esoteric? Let me just say that I've used this over and over in several papers that I've recently written that have to do with convergence of the proximal point algorithm, convergence with augmented Lagrangian methods, how to characterize second order sufficient conditions and non-convex optimization and so forth. So this is a fundamental fact that can be used. Now, brings us back a little bit again to what we were talking about earlier, that we have a set C, and we know all about the variational geometry of this set C on the first order, but what should we understand about it as the second order aspects of a set C? And the question has come up more than once. What about looking at second order tangents to this set? They do have a role, but they're only one part of the picture, which is a certain kind of duality with what I think is, well, what I want to talk about here. So what we can use instead now is the fact that we can identify the set C with its indicator function. All right. So then what I can do is look at the second order epiderivatives of the indicator function. And it's not necessarily an indicator function. I think the reason people are so happy to look at second order tangents is they have an inner idea that at the second level in geometry, the second order object you associate with set C should be geometric. But that isn't even as true in differential geometry. Things like curvature are aspects that are numerical. They're not geometric. They have to be captured by numerical quantities, not geometric figures. So anyway, what does it do here? So here's where we can look at this, and this is something about the second order property of the set. So here's an example I will show you. This is just a simple example because we don't have time here to do a lot. There is much more to say here, but let's just look at the case where we have a set defined by a single smooth inequality. And look at a set, there's just a single inequality constraint, and here's an X bar for which this constraint is tight. And I assume that it's not degenerate right there in the sense that the gradient isn't zero at this point. So the gradient will give some normal to this level set. So it's a simple classical picture. And now I look at that particular gradient as the V bar. And now I look at what would be the second order epiderivatives of the indicator at that function. And what do I get? I get a generalized quadratic function. A generalized quadratic function. It's a function, by the way, whose subgradient mapping will have a graph that's a subspace. So this is a function for which the effective domain is a set of vectors W that for which the gradient is equal 0. This is the tangent space to this inequality constraint at x bar. I'm looking at the tangent space to the set C at that x bar, the tangent space to that. And then on that tangent space, I have this quadratic expression given by the Hessian matrix. So the curvature of this somehow related to the Hessian of G, and this is how it comes out, that the second order epiderivatives are giving the curvature in that sense, are reflected in this. So, but a companion example is, well, what if you have a set without curvature? Well, the sets that have no curvature are exactly the polyhedral sets, let's say. In this case, let's think of a polyhedral convex set. And let's look at a point, at a normal vector to this at some point. And then it turns out that then we do get an indicator. This is the case where, because there's no curvature, we don't need this kind of expression. We just get an indicator. So in this case, the second order epiderivative is simply the indicator of a certain cone. And this is a classical idea of a cone. It's called the critical cone. It's known very well for linear constraints and optimization. It's the cone, it's the part of the tangent cone for which this vector vanishes. So second order conditions involving linear constraints, even nonlinear constraints, get into this kind of tangent cone, this critical cone. So when there's no curvature, then you do get an indicator on the second order level. But when there is curvature, you have to have something else. Now, I could equally well look at a more complicated system, and then we get a more complicated formula, but well, so be it. Now let's apply that to optimality conditions. You wonder, what about second order optimality conditions? So let's minimize, we're at this very general level here, which for practical purposes, then we'll have to elaborate later as a calculus. But we also always want to understand it first at the most fundamental level. So here I am just minimizing a proper lower semi-continuous function on Rn, and I'm looking at a point x bar, and I'm looking at optimality conditions connected with a local minimum. And now I am able to tell you, and give you conditions that look very close, or exactly the right substitute, at one level anyway, for the classical necessary and sufficient conditions. The first order condition, as always, is that 0 should be a subgradient. So the point x bar 0 is in the graph. Then we have necessary and sufficient conditions. And so since 0 is a subgradient, when I get to the second derivatives, I have the pair 0 x bar. So that's why I have a 0 here, since after all, the subgradient mapping may have some other subgradients than 0 at this point. So I have put, so this depends on the particular subgradient. So I look at the second order curve, and the necessary condition is that, well, all of these functions are 0 at the origin, so I never have to look at W equals 0. So for this should be non-negative in the necessary condition and positive for the sufficient condition, just like the classical theory. And the sufficient condition is, by the way, exactly equivalent to the sort of quadratic growth condition, local quadratic growth. This is a well-known and tried and true property that's used very much in studying algorithms and their convergence. Whether the local minimum has this, so that would correspond to this sufficient condition being satisfied, equivalent to that condition. And then, of course, to make this work, you need calculus rules. You have to determine the second order epiderivatives, various functions from their structure. And there's a lot of that which can be done. A lot of it is in the variational analysis book in chapter 13. And Then there's some other things that are parabolic derivatives. And this is a function version. It's actually something that's some sort of something that corresponds in a way to the geometric, what was it, second order tangent cones, but on the function level, and is closely related to them in a duality. This is all a good subject, and more recently, Boris Borhovich and his team of researchers in various places have been working on generalizing all this parabolic theory. There's parabolic regularity. It's a beautiful and important subject, very contributive, but at a certain point, we come back to the question I was raising earlier of what good is the optimality conditions? Well, there's certainly some good. For example, this case, we see that this type of condition corresponds to this simple, basic quadratic growth condition, which has a proven track record as being important in optimization analysis. But then there are other kinds of algorithms or other considerations that might want more, better kind of more stability in algorithm or something or other. So then we get to other approaches. And this is something that I'm particularly very interested in right now in a lot of recent papers, using augmented Lagrangian methods. And that involves a primal dual approach where we are able to devise a very generalized idea of an augmented Lagrangian. I'm still working on it. I have more papers in the factory line that I haven't yet written up, and then it has to do with looking at saddle points and that. So anyway, that's a big subject which I hope I could get you interested in. So we're reaching an end at this lecture, and all I want to do is make a couple of comments here that set convergence is you find in this chapter 4 of the variational analysis book, and it also includes things which I didn't describe here, but are related to these cosmic limits. You have to have what happens with unboundedness. There's more that can be said because a sequence of sets can converge out to the horizon of space. Horizon points, I have these direction points, and direction points can be parts of the limits. And in the end, that plays a role with things like horizon subgradients as well, and the graphical convergence. So in the end, that's necessary, but I didn't include it in the talk. And the graphical convergence and what it all means and how it relates to everything is in chapter 5 of that book. The special results that I talked about convex functions, though, are later. Weismann's theorem, Polikan's theorem, Latouche's theorem, and so forth. Then there's the second order theory is mainly in chapter 13. And then finally, if you are interested in this other kind of thing connected with augmented Lagrangians, then I suggest you look at an article to start by looking at an article that's on my website, which I list here. All right, that's the end of my lecture for today.
Thank you, Terry. Let's see if any questions from the audience. Yeah, you can put the message in the chat and then I will ask. Maybe when we give them some time to think about the question. Terry,
We have a lot of time.
Yeah, what is the second order EP derivative? Is it also called second subderivative? Is it the same?
Yes. Maybe I'm using these terms loosely. Sometimes I forget which exact term I used in the book. And then when I look back at the book, I remember I've been using subderivatives as in one way as a kind of a subderivative.
So we just call it second subderivative without.
Yes.
Okay.
But the problem is that there's also the parabolic ones.
Yeah.
Which, well, those are parabolic epiderivatives. I don't know. That's have to forgive me for not remembering exactly the terminology I invented.
Too many.
There's a lot of things here, and it's important that Epi come into this, because one thing I've seen over and over in the years is people tend to fall back on simple ideas like taking directional derivatives simply along line segments, and that is not adequate for anything. Even if you have finite functions, it doesn't work. You really have to use these epigraphical concepts at the second order level. And it's even true of people who are very advanced, and like Boris Monotonicity. I think although he in principle he liked the idea of epiconvergence, he didn't really embrace it as his own importance for him until a later stage. Now he really likes it. And he does everything with epiderivatives. But a lot of people, you know, it is a new thing. It takes a while. So while we're waiting for questions, let me just maybe give you a little bit of an anecdote again. So I've had such a long history. I wrote the book Convex Analysis. Now everybody knows that this is a book with so many references, one of the most referenced books in the history of mathematics, and it's still being sold after all these years. But what was it like at the beginning? How did people think about it in the beginning? It wasn't so well received. So I already told you some stories about that people were disappointed. My colleague at the University of Washington, Bob Phelps, who worked in Banach space theory, he was disappointed that it was only finite dimensional. Although the whole book is so big and complicated. What if I had to do everything in infinite dimension? It would be incomprehensible. You first have to know what it is in finite dimension. So that was an important part. But you know, then what about my colleagues in optimization? So I've been asked, it's interesting always to respond to this question, are there applications of variational analysis to optimization? Well, variational analysis is inspired, designed exactly for such applications, that grows out of and supports such applications. But so did convex analysis. But what did the people think about it then? When I first had that book, you know, or even before the book was out, I went to conferences. I could describe duality theory when you would use conjugate convex functions. And you know what the reaction of people was? They said, well, they're polite. This looks nice, but you know, behind that, you see they're all saying, this looks nice, but it's very theoretical and nobody will ever use it. Nobody will ever use convex analysis. It's too complicated. Nobody wants to study a new subject. We already have calculus. This was very much in mind. It took years. It was 10 years or more before convex analysis really started to catch on, and people realized that they needed it. And so maybe it's that way with variational analysis. Variational analysis has been around a couple decades, but it took convex analysis that long, and now I do see a lot more interest in variational analysis. People are coming to understand it, but it's a lot to learn. It's, you know, we don't learn it at an elementary level. The whole ideas are different. So that's what I'm trying to do in this talk is to give you an easy way to see the context of the ideas and why they're worth studying. All right, now I see we have somebody chatting.
I think I can ask a question first, right? Okay. So, Terry, that's a wonderful talk again. I think rational analysis is used in computations in all my studies. So don't worry, there's people will take time to accept the rational analysis from very beginning.
You mean papers? Yeah, you mean papers about analysis that refer to results there? Yeah, okay.
Yeah, the second order rational analysis is about computation.
Okay, very good.
It's not theory, it's about computation, in my view. Okay, so that's my understanding. But here is a question, more technical question. You talk about second order conditions as a local minimum at X bar. For sufficient condition equivalent to the second order group condition, right? But here, do you need any constraint qualification? I didn't say it.
No, not at this level. You don't need, what you will need, where do constraint qualifications come in? They would come in in the calculus when f is given by some other functions. So for example, if f is now the sum of a smooth function, a C2 function f0, and the indicator of a set, then
Mhm.
I need to know how to do that, and a constraint qualification will come in. But actually, the constraint qualification in that example is automatically satisfied. But what if I have some chain rule? I have to know how to translate the
Okay.
second order conditions, and that's exactly why you need it. But at this abstract level, no, you don't need it.
So I'm thinking that we are going to apply this theory to constraint optimization. That's our goal, right?
Well, when you say by constraint, when you say constraint optimization, you mean that properties of the effective domain of the function need to be made explicit. So I need to know. So the question is, here I just have an abstract function f. I have said nothing about its structure, but these theorems are true. But now you mean, what if this is specific? Like I'm minimizing a function over a set C.
Yes.
Let's suppose this was a C2 function f0, and I'm minimizing it over a set C defined by classical nonlinear programming constraints.
Mm.
Then I need to know what are the second order epiderivatives of the indicator of such a set C.
Mm.
And actually, I gave an example in the case of a single constraint. Maybe we should go back to that for a moment here, because I think it's kind of interesting. So let's go back. Where did I hear? Go back here. Yeah, so here I have a particular set C. Set C given by a single constraint. And now suppose I want to minimize over this set C a function f0, a C2 function. So now I'm looking at the case where f is equal to the sum of f0 and the indicator of C. And then I apply those second order optimality conditions to f. But then I have to know what they mean in this case. So in this case, then I have to, and it turns out because the first function f0 is simply quadratic, when I get to second order aspect of that will just be its Hessian expression. It's quadratic Hessian expression. But what about the second derivatives of the set of the indicator? Well, here's what I would get in the case of C. And it turns out there will be something like a sum of these. So what I will have is an expression that involves a Lagrange multiplier and something with this. So anyway, you see that somehow the Hessian of this constraint function will have to be a partner to the Hessian of the function I'm minimizing as part of the second order condition. And this is just a simple indication, because if I have if I have this like a whole constraint system with equations and inequalities, then there would be, of course, a constraint qualification, as we would need even on the first order level. We need a constraint qualification, but then there would be a normal cone formula. In that case, there's the exact formula. And this is all in the convex variational analysis book, by the way, in chapter 13, these formulas for these particular cases. So the calculus of second derivatives would, in that case, exactly come down to elaborating this into the kind of condition you would like. It would be a form of necessary and sufficient condition. But I'm arguing that although this is good, it's not the end of everything, because there are some applications for which more stability is more interesting. And actually, even in nonlinear programming, the classical second order conditions are stronger than just this. So that should all be in this other paper on, if you look at this augmented Lagrangian paper, it drives a different, a kind of a more restrictive form of second order condition, in which I have something like a more stable, so like a second order condition like this, which isn't just at this one point, but it sort of works in a sort of a local way. So it goes just beyond a single point. So that obviously could be more important for some kinds of algorithms. It's greater stability that you would have in counter. But for that, you get a different thing. But in classical nonlinear programming, actually have that already from the strong second order conditions. And that's all explained here in that paper.
Okay, Tyrrell, I got it. We need more work, right? To get more.
Well, there's a lot of work to be done in the second order theory, right? There's so much. And yeah. I know Gene was working on some second order things. There's a lot that could could be of help in this kind of, and much more generality than, you know, there's only so much time has passed to work out these ideas, but the rudiments are very fundamental. There's no way that they can't be involved somehow in further theory. It's not that there's something better exactly, because these are just too fundamental. As you could see by those theorems, the Touche's theorem, this is just a very fundamental thing that has to be the building block, some way or another.
Okay, thank you, Terry. I got it.
Okay, all right.
Yeah, Jean, there's a question. So.
Yeah, still, yeah. Maybe ask another question. Can you turn to the page we saw with the geometric connection with curvature?
Yeah, okay, go back to that page.
Previous one, yeah. Oops.
That
Yeah,
one?
yeah, this one. So what do you mean by this first order? First, this is first directive, right? Is this is
you know, I defined the subderivatives of a function f.
Why this is an indicator?
I'm looking at a set and I'm asking how to apply all this differentiation in a geometric way. And so I'm choosing to look, I'm specializing, I'm applying the general theory of first and second derivatives of a function to the special case of the indicator of a set. Because this is my way of applying the theory of differentiation in a geometric setting.
Yeah. So this is the first order, right?
If I have subderivatives, and you know, all of that for a function, and what do they mean then for this?
Mm-hmm.
And this was already in an earlier lecture. I showed that if I look at this first order, so this is like your directional derivative. This is the kind of directional derivative we have in variational analysis, a better directional derivative, not just along lines. So this directional derivative function, if I apply it to an indicator function, what I get is the indicator of the tangent cone.
Yeah.
That's what I meant here, that this function is an indicator. It's the indicator of the cone to C at the point x bar, this directional derivative function. But when I look at the second derivatives of the indicator, the indicator, I don't get an indicator. It usually isn't just an indicator. And so then I gave these examples. Here, if the set is polyhedral, then the second derivatives do give me an indicator function. They give me the indicator of the critical cone that we know from optimization theory. But if the set isn't polyhedral, then it has some kind of curvature. And in that case, the second derivative has some curvature aspect. It quantifies in some way the curvature of the set. And this is an example showing in the case of a single smooth constraint that the second derivatives quantify the convergence numerically. They involve the tangent cone at this point, but then they could quantify it with this quadratic term, the curvature. And then I was just if I have more constraints, like a whole Kuhn-Tucker type nonlinear programming constraint system, then there's similar formulas. So the indicator of or the second derivatives of the indicator would apply that. And where would I get these? Well, if I'm going to minimize, for example, F0 plus over a set C, it means I'm minimizing the sum of F0 and the indicator. So then I calculate the second derivatives of those, and then that's for the convergence. And that's how I get actually a second order Lagrangian condition.
But this looks like kind of indicator function, because here you have.
It's not an indicator. This isn't zero. This is a quadratic function, unless the Hessian is zero.
It's not indicator.
If zero, then I don't have much curvature. Hessian could be zero right at that point. Then this would be zero.
So be something plus an indicator function.
Yeah, if it doesn't have it, it has an effective domain. The effective domain is described here is the tangent cone to this set C at this point. The effective domain isn't necessarily always the tangent cone. Could be smaller, but in this case, the tangent cone to the set given by this constraint is this hyperplane. It's the tangent hyperplane. And then on this tangent hyperplane, I have a quadratic function that's quantifying for me the curvature of the set at that point.
Tyrrell, what do you mean by curvature? Do we have any definition?
I may be using the term loosely because sure there's some classical notion of exactly what the curvature constant is. So I don't want to be technical about what the curvature constant is. What I do mean is that when we have a set which isn't polyhedral, polyhedral sets have no curvature.
Okay, that's fair enough. Thank you.
Polyhedral, then when you look at these second derivatives, you're going to get non-zero quantities.
Yes.
And these non-zero quantities, this is a positively homogeneous function of degree 2. And that positively homogeneous function of degree 2 is going to describe something about how the set curves.
This is just like a STP cone.
Enter in the optimality condition, because if I look at the second order optimality condition, after I calculate it and use this, then I'll be looking at the sum of the Hessian function and this kind of function with some multiplier. And that way I will end up with a, anyway, I'll end up with something like a second order Lagrangian condition. Second order optimality condition that would look familiar.
Yes, Terry, when C is the STP cone, that exactly you get something similar.
What second order cone?
Yeah, it's a semi-definite programming cone, STP cone. You would exactly
second
get
order
the
programming cone would be, that's right. So this is, by the way, this is a big area, I think, where people could do a lot of work. No, people are not really very much exploring the variational theory of the second order cone.
Actually, it's much used in the semi-definite programming research. It is indispensable.
And I guess it must have some kind of curvature.
That's right.
I don't know the answer to this, Stefan.
Yeah.
I don't know the answer to this. It must have an answer. It probably has a beautiful answer. This is a really good question to raise. What if C is a second order, is that a semi-definite cone? Then what are the second, these derivatives? What are the second order epiderivatives? That's a really good question. It probably involves classical matrix theory in some way. As I mentioned to you before, Jim Burke, my colleague Jim Burke, and also who am I thinking of? Michael Overton, they worked a lot on eigenvalue problems and optimization. Eigenvalues, you have eigenvalue functions like the maximum eigenvalue of a semi-definite matrix, or the second highest one. There's all these different, or the sum of the top three. These are various functions which are actually convex. Well, no, they're not. Well, I can't remember exactly. Anyway, you have to use some, not just convex analysis to understand them. And they tried to understand whether they were variationally regular, for example. And they aren't always variationally regular, but I can't remember exactly the full results of what they got. But the properties involve very classical kinds of ideas of eigenvalues and special kinds of matrices in order to calculate tangents and normals, but nobody has done the second order theory for this cone. That's a really good topic. There must be something fundamental there.
Terry, I think people use the second order parabolic derivatives of the largest eigenvalue.
They could do that. That's good. Yeah. That's good. That's good. All right. Then what I should look at in chapter 13 is the duality between that and second order epiderivatives.
Yeah.
That's a beautiful, beautiful thing. This is there's something called, I forget, parabolic regularity. And I'm sure that this second order, this semi-definite cone has this parabolic regularity property, but that isn't shown there in the book, and I don't know what the reference for that is. But then that would show that there's more. To the extent that they use these parabolic derivatives, you need to look towards the end of chapter 13, but then there's a duality. From the parabolic derivatives, you get the epiderivatives and vice versa. So that would actually answer this question. Maybe there's an answer that's right at hand, but somebody has to do it.
Yeah, I like it. Thank you, Terry.
Right.
Wasn't that connected with the parabolic regularity that Boris and recent paper study?
Yes. Yes.
Yeah. It's a
Parabolic
second
regularity.
order.
That's a term I introduced.
Yeah, in your book.
I think I may have just introduced it in that book,
Mhm.
variational analysis book.
Yeah,
it's,
so you
and that,
connect
this is
this
another
one.
example. It's like a hidden gem. So it's caught on now, but Boris is very excited about it. And it turns out he's very enthusiastic that this is just the right idea. So once you know that, then as I say, there's a duality that shouldn't be overlooked. I wrote nonlinear programming much earlier, in which I had parabolic derivatives and I used them in optimality conditions, but now, it's all part of one thing. I love duality. And if you have duality, you have two ways of looking at the same thing. So if you know those parabolic derivatives, then you know these epiderivatives. So for example, then you could apply these optimality conditions, just as I've been describing here. This is something nobody has really, as far as I know anyway, nobody has really worked this out completely. There's so much more to know. And then there was a chat message, which I looked and saw for a moment, but never got asked. It turns out I can see them. Here, I'll just read it myself. The question is whether this epigraphical convergence theory is useful for new approximation schemes and, say, stochastic programs. Yes, it's certainly true. I'm not able to talk about the stochastic operations here, but yes, it's absolutely the case. And not only that, once you get into stochastic optimization, you need to understand all sorts of other things like set-valued random variables. How will you know a set-valued random variable? And how could you know a law of large numbers of set-valued random variables? Well, Roger Wetz has developed a lot of that theory with some collaborators. Look at the papers of Roger Wetz and you will find a lot. Set value, and then if you can have a set valued random variable, then you have also a set valued epigraph. You'll have epigraphs as random variables. This is getting very much into looking at stochastic optimization problems. Well, using like a second order. Okay, your second order optimization problem is given by a random epigraph. And then you have to, how are you going to analyze that with algorithms? You're going to need to know things about convergence. What happens in the limit? Like law of large numbers. Your limits are very important in all of probabilistic analysis. To what extent does the empirical version converge to the real version? All of that will necessarily involve epigraphical convergence in stochastic optimization. There's no way to have a solid theory of that without using such convergence. It would be a delusion. But there's so much to do. People haven't really done that.
Yeah, I see there's a question answer part I didn't see. Good that you found
Yeah,
this.
there was one chat. I see a little thing that had a number one chat.
Yeah, there's a different part. One is chat. I was keep looking at the chat, but then this is from the question and answer.
Yeah. Well, as always, I'm so happy.
Oh, there's one. Yeah, another one.
Explain that to you. Here's another one. All right.
Yeah. For graphs that are not second order differentiable, like epigraph of x^3/2, do you have any suggestions to describe their curvature? Is it meaningful to define holder?
Sure. There's nothing wrong. You would have to figure out what the second order derivatives of this are. Second order epiderivatives. I think it has second order epiderivatives because that doesn't depend on it being differentiable. But you have to remember that the second order epiderivatives depend on choosing a subgradient. So in this case, you'd have to choose subgradient 0 or some other subgradient. And what would happen? I would have to work out the example to see. But second order epidifferentiability only uses a subgradient, but it depends on a choice of a subgradient. Or you could say at a given point, you have to look at, you get a different second order epiderivative function for each subgradient, and the collection of all of those describes a second order behavior at this point, but it doesn't require the function to be differentiable. Not to mention second derivative doesn't even have to be first differentiable. But there's another aspect of this. This kind of function is a function that actually is variationally convex, in a sense that I haven't been able to talk about here, but it's tied in with what I've been working on recently because if you look at the derivative mapping for this, you would find that you get a mapping which is not monotone in the large, but it is locally monotone around the origin. So it gets into this other kind of theory. So there's a lot in this direction. We can deal with all of this things. But in some ways it might be, well, I don't know. That's enough said.
Another question here.
Yeah, okay.
Oh,
What I recommend beginners to read the book Variational Analysis. Okay, and it's a strong tool and so on, but how should you read it? Well, I've been trying to do it in this case here. So why don't you follow the plan of the lectures that I've been giving? So in each lecture at the end, I've given some hints on what first to do. They're not very complete. What you should do to begin with is read most of chapter 1 because it has such basic ideas and concepts. Then there's convexity, but you could skip that. You probably know something about convexity. And you can skip chapter 3 and chapter 4 and chapter 5 pretty much at the beginning and go right on to chapter 6 if you can. And well, okay, but if you go through these lectures, you already have some of the background that are in those intermediate chapters. Anyway, at the end of each lecture, I've given some hints of what you can do and what you can skip. And I suggest that you do that. Now, the final lecture tomorrow, it also brings in the other book that I have with Ascendonchev, with other kinds of ideas like implicit function theorems. And that would require something different. But they're variational. I realize that it looks like too big a job to learn. It's such a big, there's so many details. Now, the book is also organized where the various sections are given stars, which says you can certainly skip those. But to go through and just skip the star things would be if you really want to learn the subject in a fundamental way from the very beginning. But it isn't always the best way to learn something. The best way sometimes to learn something is to skip ahead and then go back if you need something that you skipped. So I suggest that you try to get as quickly as possible to the chapter on variational geometry because everything else follows from that. All these other conversions, all the ways to differentiate all these other tools of calculus, they all really come out of the variational geometry. That's really just at the heart of the whole thing. And also understanding that without convexity, you need two kinds of normals, two kinds of tangents. That's the thing to focus on at the beginning. I hope this helps.
I think time is up, I think.
Yeah. Okay. Well, there's still tomorrow. We have one more time, and I'm very much looking forward to telling you about some other wonderful ideas.
Oh.
Yeah, thank you, Terry. Thank you.
Yeah. Very good.
Okay.
Thank you, Terry.
I'll see you tomorrow. Okay,
Goodbye.
bye-bye.
Yeah.
Bye.